Hey, and welcome to the lesson on natural logarithms. In this lesson, we'll be talking about the significance of the natural log and what it means. So we're going to define the natural log, and we're going to talk about its inverse as well. Here's a graph of the natural log and its inverse, which is e to the x. So in red, you see y equals ln of x. In blue, you see y equals e to the x. And in green, you see y equals x, which is the axis of reflection. So the natural log and its properties are exactly the same as any other logarithm and any other logarithmic function. The special property of the natural log, or as you can also say the ln of x, is that it is simply log base e of x. It's written as that below ln of x. So they are the same thing. You'll see it more commonly used as ln of x. It is log base e, and e is a number that we'll talk about on the next slide. E is a transcendental number, meaning that it never stops. It's approximately 2.71828182884, and it keeps going on and on. It doesn't stop. It's an irrational number, kind of like pi. It's a transcendental number. That's the official name for it, and it's commonly used when working with exponential models, such as exponential growth or exponential decay. Just like with any other logarithmic function, if I have a log base of a number of that base to a certain exponent, since they are inverses of each other, those will cancel out, and you're left with just the exponent or the power. So the ln of e to the x would just be x, since they are inverses. And it's important to remember that the natural log and the number e raised to a certain power and used in an exponential function, they have the same properties as any regular exponential function or logarithm. So in this video, we talked about the natural log used as log base e to the x. We defined its inverse, which is e to the x. And so those two are used together to model exponential equations and exponential models.